Hey, welcome to the last presentation on parametric equations and calculus, and this one will really excite you here. Have a look at the word in the middle here, related rates. Yes. So, what are rates of change? Well, rates of change are derivatives, aren't they? Or derivatives measure rates of change. And what's related? Well, some quantities and how they change might be related. We're going to be looking at time, so that's the practical aspect, how things are changing with time. And that's important here. Let's have a look around the screen. Maybe the feet of a ladder are slipping away from the wall and the top of the ladder is coming down, sliding down the wall. At what rate would that be coming down? And what about filling up a swimming pool here? If we put in an amount of water at a certain rate, that might be a rate of change of volume, mightn't it? And we want to know how quickly here the height of the water or the depth of the water is changing. And perhaps sand falling off the back of a truck there, the rate of change of the volume and how quickly this height builds up, or filling up a triangular trough, something like that. So it is an exciting application, and let's have a look at how we go about this sort of stuff. So I've got here from Hayes and Harrison clippings, and here's that first problem where we have the top and the bottom of the ladder moving, and it's a 5-meter ladder. Just remember now, when you're doing problems like this, or any problems, you must use all the given information. Okay, so make sure you put that on your diagram in a minute. So generally, we have a question. If the end of the ladder is slipping away from the wall at some known rate, at what rate is the ladder moving down the wall? That's our question. And you might see that we have to put a bit more detail in it than that in a minute. But for the moment, what sort of steps would you go? How would you go about the problem? What sort of steps would you use? So I reckon the first one is this. Make a mathematical model, of this practical situation, a mathematical description. Here it is a well-labelled diagram, and we've put in the 5 meters, and we know that these two things are varying. So it's important to use pronumerals there to remember that as x changes with time, so will y. So x is some function in time and y is some function in time. Okay, so we can see that that's going to incorporate the changes of those things quite well. Let's go down, and what else could we do? What do you reckon? Well, we're going to have to identify the quantities which we're interested in. Well, here we are. We want to see the rate of change of y, rate of change of x. So the quantities we're interested in are x and y. Identify the variables or the quantities. So that's x and y, because we want later on to have dy by dt and dx by dt. Okay, we want to see how both those quantities are changing with time. Okay, let's go down and see what can we do next. We could find a formula connecting the quantities. I like students actually write in connect x and y. So it's just a reminder. And here, of course, it's an easy connection because of this right-angled triangle. So by Pythagoras, the square on the hypotenuse equals the sum of the squares on the other two sides. Pythagoras there. So we've got a formula, and guess what we're going to do? I think you've probably seen through the basic solution now. Because we want a rate of change, we're going to differentiate with respect to time. Okay. So rates of change are part of the meaning of the derivative, isn't it? So here, Huddy's dichotomy, you've got the derivative, maybe from first principle or from a rule. What's the meaning of that? The slope of the tangent is one possible meaning around the dichotomy here, and the other one is the instantaneous rate of change. And that's the one that we're using here. Be flexible with how you interpret the differentiation process. Okay, so this is what we're focusing on here. So if we take the expression that we've connected x squared and y squared with, or x and y with, and differentiate it, then just remember here, this is implicit differentiation, isn't it? It's implied here, because we've got these moving parts, that x is x squared, x itself is some function in time, and x squared is a function in x. So we actually have the chain rule. We've got a function here, let's say h of x is x squared, and x is itself a function in time, which we don't know. So here we have the chain rule. We're going to have h dash x by f dashed here of t, or dh by dx by dt, if you like. Okay, so that's the chain rule applied in the case of implicit differentiation. So we're going to do that, 2x dx by dt and 2y dy by dt. There are two parts to that derivative, differentiating with respect to x, first of all, and then with respect to t. All right, and the derivative of a constant is 0. So now we can get to this point, dividing both sides by 2, and we've got a connection between the rates of change. So not a bad little trick, is it? We'll summarise this in a minute. You can take some notes. So here we are, back to our problem. It's slipping away from the wall, and what rate is the ladder moving down the wall? All right, now we want to evaluate this at a particular instant in time. So we can rearrange this expression. Okay, so subtract x by dx by dt from both sides, so it becomes neg x dx by t, and then divide by y. So we have a working expression here. If we know the rate of change of x, this one here, we can actually find the rate of change of y at a particular instant. Notice here, because it's implicit differentiation, we need to know x and y at that instant in time. We need to know those. You've seen that before when you find the derivative using implicit differentiation. The quantities are part of that quite usually as well, the actual quantity, value of the quantities at that point in time. Okay, so do you get it? Just think through it here a little. And so let's have a look now. We could evaluate this, and we notice that dx by dt, x is getting larger going this way. It's increasing, but y is decreasing. This is getting smaller as we come down here. So you'd expect dy by dt to be negative, okay? And would you get that from here? Yes, if this was, let's say, a metre a second or something, y would be a positive, x would be a positive, and the mathematics of that would give us that the rate of change of y coming down there is a negative, so it's decreasing. Remember, it's a simple idea of the derivative. It's a limit as delta t tends to naught of delta y on delta t. Okay, so what we're saying here is that's going to, if it's a negative value, that's going to, that change in y is going to be negative. It's going to be getting less. Okay, a little bit of revision of some stuff there. All right, come on down and let's summarise what we've done. What is the method of solution? Here we are. Make a mathematical model. That means, in most cases here, drawing a diagram, labelling it with all the given information, using pronumerals for quantities which vary. There's a few tricks to that. We'll have a look at some examples from Hayes and Harris shortly, and you should have their book and have a look at that. So what have we done? We've said what's varying, what are the things that we're interested in, x and y, find a formula connecting x and y, then bring in the rates of change, so differentiate with respect to time, because this is a practical application where t, our parameter, is time, and evaluate at the end at the particular instant in time. So we didn't have any numbers up in that ladder problem. That was just a skeleton problem, but we're going to do that one now. Okay, well, let's have a look at that problem and see what you think. Here we are. 5 foot ladder, 5 metre long ladder, rests against a vertical wall with its feet on horizontal ground. The feet slip, and at the instant when they're 3 metres from the wall, they're moving at 10 metres per second. Obviously, with the force of gravity, that rate of change is going to change as the ladder comes down the wall, going to accelerate down. Okay, so here's our diagram we had before, and you should make these statements. I like students to set this out as given, what are we given here? dx by dt is 10 meters per second at x equals 3 meters, and something like find dy by dt. And then even put in connect x and y, a basic solution structure there. At least that's what should be going on in your head. So here you introduce the pronumerals, they're on the diagram. Find the rule connecting them, and I'll give you some summary of some rules you can use to get this relationship. Then differentiation, implicit differentiation, be careful. And then we now have some numbers we can put in. Remembering we wrote this one, dy by dt is neg x over y dx by dt. You don't have to rearrange it, that's what we did. So we can substitute this in, and then we can substitute in the x value, and we have to go back and work out the y value there, because from implicit differentiation to evaluate it we needed x and y. So we have to go back to our original expression up here and work out what y was at that instant, and then substitute it in and come up with an answer which is neg 15, or decreasing at 7. And you should put this interpretation, don't leave it like that, explain it. Okay, so b is decreasing, y is decreasing, OB is decreasing, that is, there's your final answer, moving down the wall, because it said in words at what rate is the top of the ladder moving down as the feet move away. Okay, so that's the idea. Now an important point here, see they put this diagram, this is at the instant in time, that's 3 meters. Now some students jump the gun a bit, and coming back up here they read the idea that you have to evaluate it when x is 3 meters away. And they put 3 in here, and that would be bad, wouldn't it? Because we'd lose a variable. There wouldn't be that rate of change dx by dt to work with. Okay, so don't put in something which is not a constant value for something which is varying. Must use pronumeral and bring it in later. We'll see that again later on. So this mathematical model and identifying the variables is very important. And that's why up here, just come up here a bit, hang on. It's not a bad idea to put down the two things that are varying. So you remember that, and remember that you've got to have x and y, and you can't have a constant in here at the beginning. You're going to substitute that later. Do you get the idea? All right, come down, and let's do another one. There's a few here, some interesting ones, in fact. Okay, here she is. We must not substitute the particular case values too early. The differential equation in fully generalised form must be established first. I wonder if you realise that. We spoke about this in the last presentation. A differential equation, an equation containing some derivatives, that's all that is, and we're going to solve for one of those derivatives. Okay, so here's our problem. The volume of a cube increases at a constant rate of 10 centimetres cubed per second. Find the rate of change in its total surface area at the instant when its sides are 20 centimetres long. Notice we don't put 20 in here, otherwise we wouldn't have a problem. Okay, got to have that variable x. Okay, so what are we going to try and do? We're asked, here we're given a constant rate. So you can see one of the keys to this being this type of problem is the rate of change per second. So that you can identify it therefore as dv by dt, and we want the rate of change of the surface area, so we want dA by dt. You're going to try and connect V and A. Well, actually V and A aren't easily directly connected, so we're going to write down a formula for A and for V, and we'll do it separately and use a go-between, and the go-between will be this dx by dt. So we want this, so differentiating it would be 12x dx by dt, and here 3x squared dx by dt. You've done implicit differentiation in another course. So now we can say when it's 20, we know dv by dt is 10, so we can get from here dx by dt and then use it in dA by dt. Okay, get the idea here, because we could connect A and V. So the general method is connect the two quantities that you're going to want to use. But if you did that, A is 6x squared, so A over 6 equals x squared. Root A over 6 is x, therefore V is root A over 6 cubed. It's messy, right? So I call this a go-between problem. This is a go-between problem where you're using the one variable to go between the two quantities. So you're evaluating it at the particular instant using the known rate of change, and that's dv by dt, and then switching it across and substituting it into the other expression. Okay, so look out for that type. All right, come down, let's do another one. Here's an interesting practical problem, and there's a demo, so Hayes and Harris should have their textbook and have a look at their demo of showing how the pool is filling up. Now, this is a good example. This is the dimensions of the pool. It's 16 metres wide, so they haven't put that in. Just remember, it's something like this, so that's 16 metres wide. This is the cross-section here. It's a cross-section. Okay, how fast is the water level rising at the instant when the deepest section is 1.6 metres deep, given that the water is entering at that? Look at that and you say, oh, that's a volume. Rate of change of a volume. We've got your time units there, volume units there. Okay, so what we want to do is find a model for that. Notice how this is dangerous here. These are the dimensions, but they're varying. So in our model, we're going to have to introduce pronumerals carefully here. So come on, let's try and do this. Okay, and it looks like this now. Notice here we've got D's, not the 2, okay, because that's the maximum size. Sorry about that. So here we had, what we had there was, I think, 2 and 2. And now, of course, if we put this across here, oops, hang on, I've gone too far. So 2 and 2. If we put this across here, we're going to get similar triangles, so it'll be D and D. I don't think this solution mentions that. So just notice there, if these two are equal, as it fills up, this and this will also be equal, because we're using that part of the similar triangle in there. So just notice that. We should really explain that in our solution, why those two are equal. And of course this is a rectangle here, so that's a D up there as well. Now what do we want to do? Well, we want to connect V and that variable D. That's what we want to do. So we need a formula for the volume of this body of water here. Now that's a trapezium times 16, isn't it? Out there, remember, it's the width of that. So we need the area of the trapezium. Okay, so how are you going to get that? Well, the area of the cross-section times the depth or the width of it there. So what's the area of a trapezium? Well, we've got that length. We need this one. We need that length in there. Let's get rid of all this and just concentrate on that now. So if we're going to find this area of this trapezium, it's a half the sum of the base and the two sides, sorry, times the height there. So that we need to add this side to this one. That's all right. That's 18. But now we need this top side. So we're going to use similar triangles. Let's stop that again and go back. So to get this length, can we use similar triangles? Okay, ABE and ACD are similar. Can you see that? So you need to know a bit about your similar triangle stuff, those two triangles. So BE, which is what we want, to 20 is D is to 2. Well, they've done it slightly differently there, but whichever way up you put it. So here we've got BE is 10D. So BE to D, so this to this is 20 as to 2, CA. Okay, I'll just label this, go back over that. So here, this is to this is 20 as to that, which is 2 from before. We said before that this was a total depth there of 2. All right, so you've got to be fairly tricky here. So now we've got our volume. Well, almost got our volume. We've got the sum of the opposite sides of the trapezium divided by 2 times the depth there. And this is the height of the trapezium. That's the area. Now we need to go to the volume, and we're multiplying by the fact that this is out here 16 metres wide or something. Let's get rid of that. So it's 16 metres out there. So that's 16 metres. So it's the area of the cross section times the depth, if you like. So you get our volume. So it's a lot of work in this one. And now we've done it. We've finally connected V and D. Here it is down here. Area of cross section, all of that, times the depth of it, how far back it goes. So if we simplify that, and then we're going to differentiate. So dV by dt, constant out the front, and then this, the derivative of this is derivative with respect to d is 36, and then derivative of d with respect to t, and then plus derivative of d squared with respect to d is 22d, multiplied by the derivative of d with respect to t. Okay, so you've got to be careful in there. So then we're ready. We're ready now with our connection of our derivatives. We've said particular case we were given was 1.6 metres, and this was a constant rate of 0.28 metres cubed. Okay, so this was in, I think, let's just go back up, what were the units? 0.28 metres cubed per minute. 0.28 metres cubed per minute. So down here we're in metres and minutes. As we substitute in, rearrange it, we've got this is in metre cubes and minutes. So we've got to do, there it is, metres per minute will be our final answer for dd by dt. Then we do have to do some conversions. Okay, here, so this is going to be 0.492 millimetres, isn't it? So 1,000, put it in here, will be 0.492 millimetres per minute. Okay, and it's important to state your answer in the context of the question. Don't state the answer in mathematical language. We're solving a problem that was a worded practical problem, so it's important to state the answer in the context in which it was given. All right, hard one. Come down and let's have a look at another one. X and Y are ore trucks in a mine. 2 trucks are connected by a 20 metre long rope. That's that one, and that's a total 20 metres long, that rope. Truck moves to the left, there it is, at 0.4 metres. Find the speed of cart Y at the instant when it's 4 metres from Z. You won't put 4 in there at the moment because it's a variable. Lots of things are varying here. That's varying, this is varying, and this length of rope, the various lengths of rope there are going to, as it's pulled, will vary. So let's put all that in a mathematical model. It's just, you've got to make sure it's all included. So we've got X, Y and Z is what the book's done here, and then this length here together with that was 20, so that's 20 take Y, put in our 8. Notice we don't put in the other length that was given. What was it? Let's have a look here. When it's 4 metres from Z, we don't put in any value there for the instant, because we'll lose our variable and we won't get our full differential equation therefore. Okay, so we've list down what you're going to call the varying quantities, as well as put it on a diagram. And we've made the conclusion that this is 20 take y there, because the length of the rope is 20. Now we've got a lot of stuff to connect here, because we want to find the idea of dz by dt is what we want to find. And we've got to connect that to the given rate, which is dx by dt. So here our connection really is to connect x and z, because we want dz by dt and we've got dx by dt. But we actually have to go, it's a go-between problem, isn't it? Because we can connect y and x, but we can't connect x, y and x, and then y and z. We can't connect x and z easily. So if we did two Pythagoras's, so let's gobble this out. So Pythagoras in this one, y squared equals x squared plus 8 squared. And then in this one, 20 take y squared equals 8 squared plus z squared. Or rearranging it, z squared is that. So we're going to use y as a go-between here, between the two expressions. So first of all, let's differentiate this first expression. So it's 2y for derivative of y squared with respect to y, and the derivative of y with respect to t, and it's 2x dx by t, and the derivative of 8 squared is 0. Derivative of constant is 0. No rate of change in a constant, is there? Okay, so here then the other one, 2z dz by dt, differentiating 20 take y squared is, first of all, differentiate that with respect to y. It's 2 times 20 take y there, and then times neg dy by dt, because the derivative of what's inside here with respect to t now, because it's implicit in that variable time, so it'll be neg dy by dt. Just what's that negative in there? Okay, and derivative of constant is 0. So we've now got two expressions we can rearrange to get this here. So we've got dy by dt and dz by dt. And we can use dy by dt to come across in a minute. So what we need to do for the particular instant is when this is 4. Okay, so when this is 4, we can substitute it back in our first Pythagoras one there. Where is it here? X squared plus 8 squared, this one here. And get our x value, because if this is, by Pythagoras, this is going to be root 80, and so our y value will be 20 take root 80. And therefore we can find our x, and then use that. So finding our x value, we've got, therefore we can put it in this one and substitute those in and get dy by dt. Bit messy, this one. And then we've got to take that and put it in this one, working with these fairly difficult but practical numbers. And that's a point now that you're expected in this course to be able to work with practical numbers that aren't exactly whole numbers or nice decimals. Okay, so they come about from this figure over here, where at that instant 4 and 8, we've got that, and then 20 take that, and we eventually have to evaluate it to 3 significant figures. Okay, so what's our answer? Our answer for dz by dt, using dy by dt as a go-between between the two differential equations. There we are, using that as a go-between to get to z from x. We've got dz by dt is neg 0.617. We've just got to check our units. Everything was in, time was in seconds, and everything was in meters. So truck Y is travelling to the left at neg, so its rate of change is decreasing. This was Z in here, wasn't it? And Z is actually getting less. It's approaching that point, big Z, at the rate of 0.617 meters. So it's going that way, and it's decreasing. That length is decreasing. Well, you've seen a few now, so you've got to make up your mind. Is it possible to directly connect the two variables, or would you actually use a go-between, okay, where it's not easy to connect them? talking about connecting them and related rates, relating them, here are some math steps that you really need to get your head around. We've used all of them, I think. No, we haven't used sine and cosine rules. So Pythagoras' theorem, we've used that a couple of times. Similar triangles are important. Right angle triangle trigonometry, haven't used that. SOHCAHTOA in a right angle triangle, opposite over hypotenuse and all that stuff. And sine and cosine rules. So this is crucial that you keep these tools strongly in your mind when you're trying to connect these things, these quantities, before differentiating with respect to time. Okay, I think it's time to have a go. So here they are. Just remember the steps. Hope you've written them down. If not, go back and make some notes there. You need to look at the question, make a mathematical model, introduce your variables, make sure all the information's there on the diagram. Make sure you identify with pronumerals the things that are varying, and then your connection, and then a differentiation evaluation. Okay, so some of these are a bit introductory, so you won't need a diagram, but it's important as we go on that you do have a diagram as we come down here. So I think if you have a look at 5, I think that's a go-between problem. Anyway, pause the presentation and have a go, and I'll show you the solutions right at the end. Let's have a look. I think there's about 12 of them. 12 problems here. There's our sand off the truck one. Sometimes like this, you don't need a diagram. You've got the formula there. Think about that type. Okay, and then 9, 10, 11. We'll have a look at 12 in a minute. And there's 12. Okay, let's have a look at the solutions now. That's question 1 and 2. Three and 4. Five and 6. Bit of 7. 7. We'll just have a look at the rest of 8. There's 8. 9. 10. 'But we'll just go back up a little. Come up here. Doesn't want to go up there, so we'll come this way. There's 11. Similar triangles one. And finally 12. Well, I hope you've enjoyed that. You can see it's a powerful tool now. We're actually getting into some practical applications, and there'll be more of that a bit later on. Anyway, from me, it's cheers for now.